When you're asked to find out how much heat is required to convert from ice to steam, or from any substance that requires phase changes, you have to take the energy that it requires to go through the phase change and break those intermolecular forces. So in this type of problem, we have ice converting to steam. It's not a simple Q equals mc delta T problem, but that is involved. You really have to think about these problems in terms of the heating and cooling curve of water. So this would be maybe what the heating curve of water would look like. So here's your temperature, and here is your heat, and it is always increasing. So if we start out below zero with just ice, ice will actually you will have ice, and as you add heat, the temperature will go up until you hit 0 degrees C. And then what happens is the ice starts to convert to water. So intermolecular forces have to be broken. So instead of the added heat going into raising the temperature, it breaks intermolecular forces. So there is this flat-lined part in the heating and cooling curve, and that will stay until all of the water is converted to ice. After that, when we have only water, then the temperature will go up with added heat until we get to 100 degrees C. At 100 degrees C, water starts to boil, and we are again breaking the rest of those intermolecular forces, converting the water into steam. And that will continue until all the water is converted to steam, and then the temperature will raise again for steam. So you want to think about this in terms of, or these types of problems in terms of the segments here in this heating and cooling curve. So you have ice, then you're going to melt it, then you will have water, and then you will vaporize it, and then you'll have steam. So this will require up to 5 problems. So the first thing to do is to go ahead and make a plan. In this one, we have ice at negative 2.5, and we are going to take that up to steam at 101. So we'll start out with our plan, and I have at the beginning, so right here, I have ice, and I will have ice from negative 2.5 degrees C to 0 degrees C. Then, at this point, I'm right here on the graph, and so now I've got to melt the ice. I have to have some heat to melt that ice. Then I am here. I have water, and it's still at 0 degrees C, but I will have water from that point all the way to there, to 100 degrees C. Then what I have to do is vaporize the water, and that will take energy. And I will, so once you vaporize it, then you have steam, and you'll have steam at 100 degrees C, and in this problem I'm going to have it to 101. Now, once you have your plan, anywhere you have a temperature change, like here, or here, or here, that is a Q equals mc delta T problem. Now, where you are going through the phase changes with melting and with vaporizing, it's another equation. This one is just the amount of energy it takes to melt something, and that's called heat of fusion. So it depends on the substance. A lot of times we're dealing with water, and a lot of the equations that you will work with will also be dealing with water. And that is mass times that heat of fusion, and that is a constant that you would need to look up for water. And for vaporizing, it's going to be the mass times the heat of vaporization. And again, that's a constant for a substance. We're going to be dealing with water, and that's how much energy it takes to break the rest of its intermolecular forces. Little m is mass in every single equation, and so we're just going to solve for Q in each of those. They'll all come out in joules, and all we'll have to do at the end is add them together. You have to be careful. There is a different specific heat, which is C, for ice and for steam than there is for water. I included that on the bottom of your specific heat worksheet, so just make sure that you use the correct ones. For this particular problem, I'm going to plug things in. My mass is 21.7 grams times the specific heat of ice, which is 2.05 joules per gram degree C, times my temperature change. For this segment, my temperature change is 2.5 degrees C. Now, I'm just going to plug these in and I'll do the all in once in my calculator. My mass is still 21.7. You can assume that we don't lose any mass. And the heat of fusion for water is 334 joules per gram. It's pretty high because it has very strong attractive forces. All right, then we have water, still 21.7 grams of water, which is the same thing as 21.7 milliliters. The specific heat of liquid water is 4.184 joules per gram degree C, and my temperature change for that segment is 100 degrees C. Now for this one, 21.7 grams is my mass, times the heat of vaporization for water. Again, because it has the hydrogen bonds, it's pretty strong, joules per gram. And then the steam part, 21.7 grams times, that is a 7, specific heat of steam, which is 2.02 joules per gram degree C, times my temperature change for just this segment, which is 1 degree C. I'm going to put all this in my calculator and add all my Q's up together. The answer will come out in joules, which I'll probably convert to kilojoules. So when I add it all up together, I get 65,500 joules, which is 65.5 kilojoules. And that is the amount of heat it takes to convert ice to steam at 101, including the energy it takes to go through the phase changes and break those attractive forces.